And welcome to today's lesson. In this first tutorial, we will be able to list, recognize, and use the 5 double angle identities. We are now in section 6.5, the first part of it, and we're talking firstly about the double angle identities. What happens when we have the sine of twice an angle, or the cosine of twice an angle, or the tangent of twice an angle? And let me just go ahead and give those to you. The sine of 2 times an angle will always be equal to 2 times the sine of the angle times the cosine of the angle. That's the expansion of the sine of a double angle. So what's nice is you don't have the double angle anymore, you have the single angles here. And it's going to be 2 times sine times cosine. The cosine of a double angle actually has 3 different names. The main name is cosine squared of theta minus sine squared of theta. That's, I guess, the main one. This is cosine squared minus sine squared. Very different from the Pythagorean that we knew that had the plus sign. Of course, that would be equal to 1. This is now the minus sign, and it's equal to the cosine of a double angle. There are 2 other names. If you consider this sine squared and maybe use a Pythagorean to replace it with 1 minus cosine squared and distribute this negative and gather your like terms, you'll actually have 2 cosine squareds minus 1. So that's another name. This might be a good name to use if you only know the cosine value, because then you could use this and figure that out. This first one, you'd need to know the cosine and the sine to be able to calculate using it. The third one, similar to replacing this with a Pythagorean, if I replace the cosine squared with 1 minus sine squared, then I'd have 1 minus sine squared, or rather 1 minus 2 sine squareds. So that's the other name for this. What I definitely would do with your flashcard is put all 3 of these on the back of this one flashcard. I wouldn't necessarily make 3 different ones. I would just make one and put all 3 of these on the back. As long as you remember that when you're checking yourself to make sure you say all 3 of the names before you flip the card over. Tangent of a double angle. The tangent of a double angle is going to be equal to 2 times the tangent of the single angle divided by 1 minus tangent squared of the single angle. And these are our next identities for the day. 5 double angle identities. If we add these 5, to our grand total, now we have 36 identities. 36. Just a point of note, I don't really use the tangent very often. Like I said in the previous tutorial, the tangents can be a little bit more complicated, so I usually use sines and cosines instead of the tangent. Anyway, let's see what happens when we're the same thing I said in the previous one. Of course we're memorizing these, but we're not using these necessarily to substitute and verify identities. What we're going to be doing is trying to calculate something. So we're going to use its expansion and then substitute values into here and give me the value. Okay, so it's really applying these identities and calculating exact values. So let's look at our first situation here. We're given that the cosine of theta is equal to 5/13. The first thing I'm realizing is that this is not going to be a unit circle thing. Right? This is not one of the special sides on our unit circle triangles. And it's also in this interval. We need to talk about this because we need to know what quadrant this is. And given that information, we were supposed to find the sine of 2 times theta, the cosine of 2 times theta, and the tangent of 2 times theta. Okay, please don't misunderstand this problem. If we're given the cosine of theta, and that's 5/13, please don't think that the cosine of 2 times theta is as simple as just doubling this. That doesn't make sense. There's an angle, and we don't know what the angle is. We do know that the angle is somewhere in here, but there's an angle that has a cosine of 5/13. When we double the angle, I want to know what the cosine value would be then. We have the identity to help us. So first thing, let's just expand. Let's just look at this first problem. Sine of 2 theta, I know that that's equal to 2 sine of 1 theta times cosine of 1 theta. That's what the expansion says to do. I'm just expanding using my identity. If I knew what the sine were, I could plug it in here. If I knew what the cosine were, oh, actually I do know the cosine. It's 5/13. So I actually know part of this already. I'm missing the sine though. That means I'm going to be drawing a picture. I'm just going to be drawing a triangle. Now I do need to pick the correct quadrant. And I know that 3 pi over 2 is down here. And I know that 2 pi is here. So we must be somewhere in this fourth quadrant. I'm going to draw my picture in the fourth quadrant. The triangle is always made to the x-axis. There's my right angle. So here's my angle that I'm talking about. There's theta. Now given that the cosine is 5/13, that's like your ka again. That's the adjacent and the hypotenuse. So adjacent must be 5 and hypotenuse must be 13. So we're missing this side down here. But I do know that, again, this is one of my Pythagorean triples, 5, 12, 13. But watch out this time because we are going down into the fourth quadrant. It must be negative 12. Watch out for your SIGNs. Okay, now that I have the picture of my angle, I have cosine, I have sine, I have whatever I want. I've got tangent if I want it. So now that I've got my expansion here, I've got 2 times my sine value. Well, my sine value is opposite, negative 12, divided by hypotenuse, 13. So 2 times negative 12/13 times my cosine. I could look at my picture again, or I could look at what was given, 5/13. Maybe I'll put this 2 over 1 just so I realize that the 2 is in the numerator only. 2 times negative 12 times positive 5 is negative 120. And 1 times 13 is 169. And I believe that does not reduce, so I must have my answer. I expanded using the identity, replaced the parts with the fractions that I know, and multiplied it all together. Looking at my second one, I've got the cosine of 2 theta. Well, that one had 3 different names. And it doesn't really matter which name you want to use. I'll probably just use the main one. Cosine squared minus sine squared. That's what the expansion, that's the main expansion. And it's okay because I already have the picture, so I already have the cosine and I already have the sine. So let's replace that. Cosine is 5/13, so I'm going to take the cosine value and square it. And then I'm going to take the sine value, which again was negative 12/13, and I'm going to square it. So we've got some math to do here. Squaring 5/13, you just square each piece. So I get 25 divided by 169. Squaring negative 12 keeps it positive, so 144 divided by 169. These fractions want to be subtracted, and I get negative 119 over 169. Now our final problem is to find the tangent of 2 theta. And like I previously stated, I really don't like to use the tangent identities at this point. We've already spent time finding the sine of 2 theta and the cosine of 2 theta. And we know that the tangent of 2 theta must be equal to the sine of 2 theta divided by the cosine of 2 theta. That's just using our quotient identities. And if I already have these values, that's as simple as just saying that the sine of 2 theta, which was negative 120, 169ths, and the cosine of 2 theta, which is negative 119, 169ths, we could just do this. This is going to be a whole lot faster. In fact, even if I didn't have to find sine of 2 theta and cosine of 2 theta, if this were the only problem, honestly, I think that doing this work to find this number and this work to find this number and then dividing them is still faster than using the tangent identity. Now, how do you divide these fractions? Well, I see that the denominators are the same, so I'm just going to cancel them away, and I get negative 120 divided by negative 119, which obviously we don't need the negative signs, so we get 120 over 119. It's a whole lot faster to just use the existing values that we found and divide them correctly. I think I'm going to stop this tutorial right there. That's just expanding and replacing with the values from our triangle there. Thanks for watching. Oh, okay. And thanks for the applause.